Hey guys, welcome back to the channel. In this video, we're going to be going over inclined plane dynamics. I'll be going through various strategies and show you the best ways to set up your X and Y axis, as well as how to use Newton's second law. This will be part number 1 of a 2-part series related to ramps and block dynamics problems. By the end of this video, you'll be able to tackle any type of inclined plane and block system using Newton's second law, as well as the proper way to break up forces into components. If you find this video helpful, please like this video and subscribe to the channel to see more videos just like this. These inclined plane problems used to be really tricky for me. I found it super difficult on how to get the correct angle and therefore break up the forces into correct components. But now I've learned all the tricks and tips to make these problems extremely simple. Stick around to the end of this video to learn a much more important factor than intelligence for getting good grades. So let's go ahead with our first problem. In this problem, it says we have a 5 kilogram block placed on a 30-degree incline, begins accelerating to the bottom of the incline uniformly, and then we say ignore the effect of friction. It asks what's the normal force and what is the block's acceleration. So for this situation, what we want to do first is draw a free body diagram of the block. So what we're going to have is, well, we'll have gravity. So I'm just going to put this arbitrary point up here, and I'm going to say this right here. We'll do a better straight line. This is the force of gravity. It's acting straight down. And what other forces do we have? Well, since it's on a surface, we're going to have a normal force that's going to be perpendicular to that surface. So we're going to have this normal force like this, perpendicular to the plane. And let's write down, let's see if there's any other forces. Well, we can ignore the force of friction. So I think that's all the forces. But we do know that this block is now accelerating in this direction. So it's moving down the ramp. We're basically coming into this problem where the block is now just placed on the ramp and it starts to accelerate with a constant acceleration. We also have the fact that this is a 30-degree incline. You can write 30 degrees there. We have the mass of the block, so the mass is equal to 5 kilograms. And that seems to be all the things that we know. So, whenever I approach a problem like this, I think the best strategy is to define your coordinate axis in the direction of acceleration. In this case, we have acceleration moving down the ramp. So what I'm going to do is I'm going to say our x-axis is in this direction, and then our y-axis will be obviously perpendicular to that. So we have our y-axis here, and this is going to represent the positive sign convention. So any forces that are perpendicular to the ramp are going to be, or going up, are going to be positive, and then any ones going down will be negative. And similarly, we have forces going down the ramp or parallel to the ramp is going to be our negative positive forces, or sorry, our positive forces going down the ramp, and any forces going up the ramp will be negative. So now that we have our coordinate axis, with Newton's second law, what we're trying to do is do the sum of the forces. So I can write sum of the forces is equals to mass times acceleration. But what we want to do is make our forces so that they're in line with our coordinate system. So we're going to have some of the forces in the x direction and some of the forces in the y direction, and that is both equal to mass times acceleration. This will be acceleration in the x direction, and this will be acceleration in the y direction. So now that we have that, what I want to do is I want to show you that we have a couple forces that are going to be in line with our coordinate system. So in this case, we have, I'm just putting my coordinate axis here. I guess I'll do it in blue, a bit more visible. And then this normal force is actually perfectly in line with our defined y-axis. So now, what we can kind of tell is that the gravity component, or mg, so the force of gravity, is actually in between our axes. It's going to be a component of y and x. So if I were to show you, the addition of vectors, this is something that's very useful, especially in physics. If we have a vector, let's call it c, like that, I can say that this c vector is a component of an a vector, like this, plus a b vector. So now I can write C is equal to A plus B. And this is the kind of the tricky part, or the thing that we always want to do when we have a component going through y and x, like the plane of y and x, and we want to put it into its components so it's only in y and only in x. So in this case, our y-axis is, or our x-axis is in this direction right here. We're going that way. So we have that line there. So I'm going to write that this will be mgx. And then we're going to have a component in our y direction, and that will be mgy. So we have a right triangle here, similar to this kind of vector addition. And now we have the components in a form of mgy, so the force of gravity in the y direction, and the force of gravity in the x direction. And this is exactly what we want. So, to move forward for this is where I think most people get tricked up, and they're trying to figure out, okay, well, how do I break up the force of gravity into components? I need angles. I need to use trigonometry to get those broken up components. So we're really looking for the angle here. So this is something where complementary angles, or basic geometry, kind of helps us out. Over here, we have two parallel lines, so this line is parallel to this line. By kind of geometry, these angles are the same. Two parallel lines and a line going through them is going to result in two equivalent angles. So what we want to do here is apply this concept. So if I look at the force of gravity, not broken up into components, just the force of gravity we had initially, that is going to be this line here. And then we also have a parallel line to that over here. And that is, I'll put it a bit closer, but that's the height of the triangle. So these green lines here are parallel. And another kind of rule of trigonometry, or I guess geometry, is that the sum of all the angles in a triangle is going to sum to 180 degrees. So here we have an angle that we can find, because we have 30 degrees and 90 degrees. So if we do 180, take out your calculator, 180 minus 90, well, that's going to be 90, so that's that angle taken care of, the right angle, and then minus 30. Well, then that's going to be 60 degrees right here. So now we have that angle, and if we apply what we just learned here with these similar angles, this 60 degree angle is going to be the same as this angle right here. I'll do it in the same color, this blue here. So that's going to be 60 degrees. And through the normal force, or I guess extending the normal force down, we made another right triangle. So this is a right angle here. So if we have 90 degrees and 60 degrees, the only remaining angle, this green angle in here, is going to be 30 degrees, which matches this right here. So now we can use these angles to break up our gravity component into an x and y component based on our defined axis. So here, I want to find mgx, which is this value here, and I want to find mgy, which is that value there. So looking at this kind of bigger triangle, if we do, for the mgx, if I do sine of 30 degrees, well, that's going to be opposite over hypotenuse. So this 30 degrees, this green angle in here, the opposite side is right there. And the hypotenuse is the mg, the original mg. So we can write sine of 30 is equal to mgx, our opposite side, over our hypotenuse, which is mg. Now if we solve for mgx, we will get mgx is equal to mg multiplied by sine of 30. So that's good. That's an important step. Now we can do the same thing that we did, but now for mgy. So mgy, if we look, we're going to look at this angle again, and we're going to say, okay, well, what is mgy? And we're saying, what is mgx? What about cos 30? Well, cos 30 will give us the adjacent side here, and it's in relation to the hypotenuse. So we're going to get the cos of 30 is equal to adjacent over hypotenuse. And if we plug in our values for our hypotenuse and our adjacent value, this will be mgy divided by mg. And solving, we can find mgy is equal to mg times cos of 30. So this is really important. So now we've broken up the gravity component into an x component and our y component based on our defined axes. Now we can apply Newton's second law. So the sum of the forces in the x direction is going to equal the mass times acceleration in the x direction. Okay, so we're going to do both of these. Sum of the forces in x, max, and sum of the forces in y is may. First, I want you to look at our axes. We are saying that the object is accelerating in the x direction, right? It's falling down the ramp, and our ramp, or our x-axis, was defined to be on that ramp, parallel to that ramp. So we definitely have an acceleration in the x direction. But what about the y direction? The y direction, if there was an acceleration, it would be going above the ramp or through the ramp. But right now it's not. So what we can say is that the acceleration in the y direction is 0. So now we're going to get the sum of the forces in the y direction is equal to 0. So if we look at all of our forces here, well, our normal force is definitely in the positive y direction. And then the only other force is our mgy, and that would be in the negative y direction. So I can write 0 is equal to the normal force, positive, minus mgy. And if I solve for the normal force, it's going to equal mgy. And now we can look back here to see what our mgy equals. So n is going to equal mg cos of 30 degrees. And now we have all the unknowns in this equation, and we can solve for the normal force. So we have 5 kilograms, which are mass, times 9.8 times cos of 30. And make sure your calculator is in degrees and not radians. So I get we'll call it 42.5 newtons for rounding. So there, we found part A. So this was part A, finding the normal force. Now we can look at part B, finding the acceleration down the ramp. So here we can scroll down and say, okay, well, our acceleration in our x component is definitely going to be positive. What other forces do we have acting in the x direction? Well, it looks like, since we can ignore the effect of friction, that it's just mgx. So what we can say is that mgx is equal to the acceleration in the x direction. And what is mgx? Well, we solved that. That's right here. That's mg sine of 30. And that is equal to the mass times acceleration in the x direction. And here, you might see that there's a mass on this side and a mass on this side, so we can cancel. And finally, our acceleration in the x direction is going to be the force of gravity, so 9.8, the acceleration due to gravity, times sine of 30. And I get 4.9 meters per second squared. So hopefully that all made sense. This was without using friction. The next problem we're going to go into is with friction. So moving into our example that involves friction now, it's going to be the same problem, but we now have a frictional force. So if we read it, it's a 5 kilogram block placed on a 30-degree incline. So I'm going to write 30-degree incline here. And I'll write the mass is 5 kilograms. And begins accelerating to the bottom of the incline uniformly. So constant acceleration. So we can say that acceleration is in this direction. The incline and the block have a coefficient of kinetic friction of 0.3. So I'm going to write mu k is equal to 0.3. What is the block's acceleration? So thinking about our last question, now that we have friction, it's resisting the force or the acceleration of the block. We're going to expect a value that's smaller than our last acceleration value. And the reason is because now friction is resisting it. It's resisting the motion of the block. So that's just something to think about before we get started. So it's going to be the exact same process, just with an added force. So I'm going to draw my free body diagram, and this will be, I'll put my arbitrary point up here, and I'll say this is the force of gravity. So we have mg. We also have the normal force directed perpendicular to the surface it's resting on. So this is the normal force. And we also now have a frictional force. So now that we have that frictional force, which is denoted by this F, that is going opposite to our direction. So again, what I recommend you guys do is set up your coordinate system so acceleration is in one of the planes. So here, I'm going to say that my x direction is in line with acceleration. And here I'll have my y direction. And this is our positive sign convention. So anything going down the ramp is positive, anything going up the ramp is negative. Again, we're going to have our 30, 90 degree, and 60 degree triangle. I'm going to set up our coordinate system at this point to see what forces are acting in our y and x direction and what forces are acting in both. So here, again, we have our gravity component now in both our y and our x directions. So we're going to need to break that up. So here, again, I'm going to write, this will be, I guess I can write it down here, but I'll just write it here. This will be mgx, and this will be, I'll do it a different color. This will be mgy. So now, in this triangle, if we do our, again, I really encourage you guys to work through this by yourselves and show yourself that this angle here is going to equal this 30 degrees. So again, we're going to have similar angles like this. So theta here is going to equal theta there. So we have 60 degrees here. So that means if this line, the gravity line component and side of the ramp, we're going to have this angle in here to be the same as this angle. And then we have a 90 degree angle triangle. So this last angle in here, I'll do it in blue actually, is going to be the same as this angle, which is 30 degrees. Okay, so again, we can split up our components. So our gravity is the only thing acting in both the x and y directions, so we need to split it up so one part of it acts in the y direction and one part of it acts in the x direction. So we're going to have mgx, and that's going to equal, from our kind of previous problem, that is going to equal mg sine of 30, and our mgy is going to be mg cos of 30 degrees. Okay, so now we can do our Newton's second law. So here we're going to get sum of the forces in the x direction is equal to ma, and acceleration in the x direction. We're also going to have sum of the forces in the y direction, and that's going to be ma times acceleration in the y direction. Again, since this object or block is not accelerating up or down based on our coordinate system, we're going to say that acceleration is 0. So the sum of the forces in the y direction sum to equaling 0. So we're going to have, what's in our y direction? We have our normal force, which is positive, and we also have our mgy, so it's going to be minus mgy, because it's in the opposite direction of our normal force, which is positive. So our normal force is going to be mgy. We're going to have normal is equal to, well, if we go up here, we have mg cos of 30 degrees. And in this question, it didn't ask us for the normal force, it just asked us for acceleration, but we do have friction, and frictional force is a component, or is dependent on the normal force. So we needed to find the normal force anyway. So the normal force, again, is going to be the same as last time. It's going to be 42.5. Let me just double check that. Cos of 30 times 9.8 times 5. Yeah, 42.5 newtons. Okay. Now we can use some of the forces in the x direction. And in this situation, what do we have in the x direction? Well, we have this mgx. We also have this frictional force. And that seems to be it. So we're going to say our mgx, because that's what's defined as positive, is minus our frictional force, which makes sense because it's resisting the motion. That's going to equal our mass times acceleration, which is positive in that direction. So our mgx is mg sine of 30. And the frictional force, I'll write it over here, is equal to mu k times the normal force. So that mu k of 0.3 that we got is going to be important. Minus normal times mu k is equal to ma ax. So now we can plug all of our numbers in. So we have 5, not a very good 5 times 9.8 sine of 30 minus 42.5, which is the normal force, multiplied by mu k, or the coefficient of kinetic friction, 0.3, and that's equal to 5 times the acceleration. So now we only have one unknown and we have one equation, so we can solve. So if I do 5 times 9.8 times sine of 30 minus 42.5 times 0.3, then I'm going to get 11.75 is equal to 5 multiplied by acceleration. And so if we divide 5 from both sides, we'll get 2.35 meters per second squared. So looking at this number in comparison to our previous problem, we had an acceleration of 4.9. So with the effect of friction, this acceleration decreased, again, which we would expect. So this is kind of the overall process and strategy to solve these problems. And if you have kind of tensions on the blocks or anything like that, this strategy and this way of breaking up components will always get you the right answer. It's just going to be maybe a few more forces to add into our Newton's second law equation. So I really hope this helped you guys, and I hope this problem solved a lot of your issues with ramp and block diagrams. So now I want to talk to you about what's more important than intelligence as it relates to grades. I find that people think the majority of students who get good grades or go into more difficult programs are people that just have higher IQs, and that's just the way it is, and that's going to be stuck with them forever. But I'm here to tell you that intelligence can change over time. The brain should be looked at more like a muscle than something that's set in stone. The more you exercise this brain or challenge the brain through problems and learning new things, the stronger and the smarter you get. Think about learning a foreign language. For people that learn the first foreign language, it's difficult. But then the next one is actually easier, and the third one even comes easier than that. Again, this is something that your brain has now developed. It's developed this appetite or this ability to learn new languages. And that's not just, structured towards languages. That can be math, science, physics. It's all the same. It's just the way you challenge and apply yourself to learning new things. Your brain can even change size through proper training and stimulus. In a research paper I'll link down below, it shows that mice that were in a stimulating environment with toys and other mice to interact with versus mice that were in a bare cage, they weighed the brains of the mice that were in the stimulated cages, and they found that the brains were 10% larger than those in the bare cages. So it's much more important that you think and believe you can achieve your academic goals and improve your intelligence through constantly challenging your brain. This will lead to a growth mindset and can have drastic effects over your success and achievement over the long term. Thank you for taking the time to watch this video. It's my goal to provide as much value as I can to everyone to help streamline the journey of a student. If you guys like this content, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. I make a ton of content to help in math and high school physics, as well as improve the confidence of students over the long term. If you're looking to get better grades and in the process become more interested in what you're learning, please consider subscribing to the channel. Thanks, and I'll see you guys in the next video.